see here. I had a verse. I'll just read Romans 5:8 for us to start with. But God demonstrates his own love for us in that while we were yet sinners, Christ died for us. I think that's a good verse to remember. So, let me begin with a word of prayer then. Dear Heavenly Father, we thank you for this day. Again, I thank you for these students and just ask you to bless this class this semester. Just help us to do the best each day, Lord, for your glory. In your name I pray, Lord Jesus. Amen. All right, so if I can find a marker. Oh, here they are. We're going to be solving linear equations. What's a linear equation? Now, for the most part in here, I'm going to, keep it real. So we'll be looking at real linear equations, which means that the variables we'll be thinking of as real variables, and the coefficients will be real. For the most part, right up until we don't do that. But that'll be towards the end of the course when we study something called complex eigenvalues. And there we just have to. But until then, we don't, so let's not. So let me look at a couple of examples that are, I think, illustrative of how it works. So if we could have like y is equal to, let's say x plus 1, and y is equal to 2 minus x. This is two equations and two unknowns, right? Example 2, you might have something like, x plus y equals to 0, and x plus y equals to, 1. Example 3, I might have something like y is equal to 3x minus 2, and 3x minus y is equal to 2. All right. And you should leave yourself room to make a graph for each one of these, okay, guys? Example 4, we might have something like y is equal to x plus 2, y is equal to, 2x, and y is equal to 3 minus x. All right, so examples 1, 2, and 3 would be examples of two equations and two unknowns. And the third example would be an example of three equations and two unknowns. All right? And we can't always do this, but for these, since we just have two variables, we can take a graphical approach, right? You guys know how to graph a line? Yeah? So let's see here. What's this first one look like? How about this one? Let's see here. So the first equation I'll do in red. You've got a slope of 1, a y-intercept of 1, so it's something like this, right? There's your y equals x plus 1. First equation here is just solve for y, right? Y equals minus x, so it's this guy. That's the same as x plus y equals to 0. Here I've got a y-intercept of minus 2, a slope of 3, so it's something like this, right? And this guy, y-intercept of 2, slope of 1, something like that. All right. Then my second equation for example 1, I've got a slope of minus 1, a y-intercept of 2. So it's something like here. There we go. That's y equals x plus 1. It lived a good life, but its life is over. Is there a trash can over there? Yeah. You don't have to get up, it's fine. But. Here we go. Let's see here, this one, y equals to 1 minus x. So 1 minus x, so it looks like this. Yeah. X plus y equals to 1 is that guy. Let's see here, this. Let's see, if we solve this for y, what do we get? 3x, well that's embarrassing. So that's just the same crooked crooked line that I've already graphed, right? Y equals 2x, well that's got the origin, and it's got a slope of 2, so it's something kind of sort of like this, right? Let's see here. So let's see here, for the last one, there's also what? One other line, right? Which I'll do that in green. And so that one, y equals 3 minus x, so that's got a y-intercept of like 3, which is maybe up here, and something like that, right? All right, so let's talk about it. Is there a solution to these problems, right? Now, I think graphically you can see in example 1, right? There's a solution, right? How many solutions are there in example 1? Just one. What does it mean to simultaneously solve several equations at once? It means that each one of the equations is true at the solution, right? So the solution here is a pair of values, x comma y, and I can graphically see that the solution is right here, right? That's the solution, right? And what is that? Can you guys tell me? I mean, I can't tell from my graph, right? If I did it on graph paper and I was super careful, maybe you could. But let me suggest that we could solve it like this. We've got both of them are equal to y, right? So we can say y equals y essentially. I mean, why not? So that gives you x plus 1 is equal to 2 minus x, which gives me 2x is equal to 1, which gives me x is equal to 1/2. And y is equal to, what is it? Pick whichever one you want, either 2 minus 1/2 or 1/2 plus 1. Either way you slice it, you get 3/2. Yeah? Did I do something wrong?
Yeah, that's what I was going to say.
Oh.
Y is 3/2.
Oh, good. Yeah, gotcha. Sorry, so the solution is a pair. Thank you. 1/2, 3/2. And yeah. All right. So the solution's unique, right? And this is an example of a consistent system. So it's consistent, and the solution is unique for this one, right? Example 2, what's the story here? What's the solution? Is there any point which is common to both of these graphs? Well, no. So here, this is an example of an inconsistent system. It's inconsistent, and there's in fact no solution. No solution. You could say this also, the solution set is the empty set, which maybe you've seen as like a pair of curly brackets with nothing in it. I can't do curly brackets at that point in the board, oh well. All right, so that's an inconsistent system. There is in fact no solution. Example 3, how about this? Is this consistent or inconsistent? Well, it's consistent, right? Solution not unique, right? The solution is not unique, and essentially the solution is given as follows. We've got x comma y, such that y is equal to 3x minus 2, and x is a real number. That, you guys know what x element of R means? Are we good on that? If not, you can talk to me about it after class. It's not a big deal. That just means that x is a real number, y is subject to that. Another way you could write this. So here, this is the solution set, right? Solution set. You could also write it like this. X comma 3x minus 2, such that x is a real number. You could build the formula for y right into the characterization of the arbitrary point like that instead. Okay? And that's as far as I'll go for the moment. But this is an example where we have consistency, but the solution is infinite, right? It turns out that's it. This is it. This is all that can happen over a field of characteristic 0, whatever that means, over the real numbers. This is it. This is all that can happen. When you have a linear system, either you get a unique solution, all right? You get no solutions at all, or you get an infinite solution set. Those are your three choices. It can never happen like with the quadratic equation where you get what? Like just two distinct solutions. Like that can't happen here. So linear equations are kind of boring in this regard, all right? Now, if you have linear equations which were made from some sort of like substitution, well then other things could happen. All right, I'll show you that in my next example perhaps. So this one here, what's the solution? Is there any point which is common to all three lines? It kind of makes you wonder, right? Is it just my graphing? Is it actually, do these actually conspire to meet at one point? I wasn't trying for that, but it would be my luck for it to happen, right? How can we be sure that those don't actually join at a point? So pretty much you just like, with our current technology, you just kind of work on the equations to make logical deductions. So like here, y equals y, right? So what does that give me? Since y equals y, from the first two equations, I get x plus 2 is 2x, which tells me what? X is equal to 2, right? But then, so that tells me then that y, from the third equation, 3 minus 2, which is equal to 1, right? Yet y is equal to 2x, which is 2 times 2 is equal to 4, which is not equal to 1, right? Now, you should write more words if you're going to solve the problem like this. You won't. By the time this problem appears on test 1, you'll have other ways to communicate your logic. You probably won't be doing it the way I'm doing it right now, so I won't belabor it. But in fact, my graph is correct. There is no common point of intersection, because when we try to solve all these equations at once, we find that they're inconsistent, right? We can't logically solve them all at once. Now, an interesting question that you could ask, right, would be something like, okay, so I can't solve all three of these equations. What's the best approximation for the solution, though? Like, what point is closest to all three at once? You know, is that a problem we can solve? Not yet. Maybe towards the end of the course we'll solve that problem, though. All right? So there are techniques for approximately solving linear equations, which we actually can solve in here, without calculus as well. So you already had a method for approximating, for like finding, you know, like a best approximation for something using calculus. But I'm suggesting that there are non-calculus ways of finding the best approximation for a linear system which is inconsistent. Are we good? All right, so you guys probably saw some of this stuff in like middle school, I don't know, high school, where? I don't know. You're like, I never went to school. I mean, I accept it. Let's see, where was I? Can I erase this stuff? All right, wait a minute. Maybe I can use this board. There's a board over here, right? What? This is a new chair. This is an unwelcome development in this room. Man, that thing is really heavy. There. There we go. Example 5. Let's suppose we want to solve x plus y minus z equals to something. And then let's say y plus 2z equal to something. And then let's say 3z equal to 9. We'll make this equal to 10 and this equal to 11. Let's see about solving this equation. Now here, at this point, I no longer want to commit to a graphical method, right? Because while all of you guys have had Calculus 3, I think. Is that a correct statement? Has everyone here had Calc 3? No, okay, there's one. Just you?
I guess.
I mean, it can happen. Are you currently taking Calc 3?
No.
See, see, this is, it's, yeah, I mean, it's okay. So, my apologies. Yeah, my apologies, but I'm going to pretend that everyone's had Calc 3 in here, but I will happily explain anything which is too mysterious. But in Calc 3, one of the things you learn is how to visualize three equations, like a linear equation with three variables. The meaning of it is it's a plane in 3 dimensions. So here, I'll just tell you. So this x plus y minus z is actually the equation of a plane. It's a plane. And the normal to the plane is 1, 1, minus 1. All right, like that's the equation x plus y minus z equals to 11. So if we have one equation in 3 unknowns, that gives us a 2-dimensional object, which is a plane, and that's its equation. That's the meaning of the coefficients. They're the normal to the plane. I don't think you need that to solve any problem in here, but it does give meaning to what we're doing. My point to you is each one of these equations can be understood geometrically to be the equation of a plane in 3 dimensions. And so when you're asking how to solve 3 equations in 3 unknowns, you're asking the question, is there a common point of intersection between those 3 planes? Right? And this is one of the reasons you should get the textbook, is because Lei has lovely pictures which show you different cases. And his pictures are better than the pictures I don't have in my notes. So, yeah. But geometry aside, so geometry helps us to understand what we're doing, but it doesn't typically help us to actually solve a problem. How do you solve this problem? Any ideas? This is like a system of 3 equations and 3 unknowns. I wouldn't even it wouldn't even trouble me a little to give this to a Calc 2 class. Because this is easy, right? How do you do it?
Start by finding z.
Yeah, exactly. We kind of work our way back up, right? We use what's called back substitution. So they're not, I mean, the stupidest kind of system of equations is like totally uncoupled, right? An uncoupled system would be something like x equals 1, y equals 2, z equals 3. What's the solution? 1, 2, 3, right? It's kind of dumb. Our ultimate goal is to uncouple the equations so that we can just read solutions off of. But anyway, let me just finish example 5 here. So we start with equation 3. And let me start numbering these. 1, 2, 3. I'm just using Roman numerals because it makes you uncomfortable. Really no reason. So z is equal to 9 over 3, also known as 3. Now from 2, we get y plus 2 times 3 is equal to 10, which gives me y is equal to 10 minus 6, which is 4. And then we can go to 3, and we've got x plus 4 minus 3 is equal to 11, which gives me x is equal to, I don't know, 10? Oh, thank you. Very good. So, and this is kind of a dumb thing, but it's important, which is that this given system of equations, right, is equivalent to the system of equations, a very silly system. X equals to 10, y equals to 4, z equals to 3, right? The system I wrote in red is the same as the system that I gave you here, right? Going back to that question of geometry, it turns out that these 3 planes in 3 dimensions do in fact have a unique point of intersection, right? So this is called back substitution. All right. Let me illustrate another solution method, this time with something a little bit different. What if we had something like x squared minus 2y squared equals to 10, and x squared plus y squared equals to 7. Now I just made these up, so they may well not have solution, and that's fine with me. I'd prefer it, in fact. Now that I've said I prefer it, it'll have a solution. That's just like a law. How would you solve this? Now let me suggest there's another way we can think about things. we can add equations, we can subtract equations. So, like this, the way I would do it is I would subtract these equations. And by that I mean we subtract the left-hand side from the left-hand side, we subtract the right-hand side from the right-hand side. This is an allowed thing we can do to equations and not change the solution set. When I do that, it eliminates x squared, and we're left with minus 3y squared is equal to 3. Yay! So y squared is equal to minus 1, which is, of course, impossible. If y is a real number, right? We can't have a square of a real number be a negative number. So unless you want me to give up on keeping it real, there's no solutions here, right? Now, what would have happened if I'd flipped the 10 and the 7? If I'd flipped the 10 and the 7 instead, we would have gotten y squared equals to minus y squared equal to 1, which would have given us 2 values for y, right? And then when you plug that into one of the other equations, you would get correspondingly 2 values for x. And so for this problem, you'd actually get 4 solutions if it was like a consistent one. But that's because this is not a linear system, right? This is an example of 2 nonlinear equations and 2 unknowns. All right, that was supposed to be unknowns. I tried. All right. So let me show you guys another example. So so the answer there was no solution, all right? So example 7. What if we were up against, let's say, x plus y plus z equals to 2, and 2x plus 2y plus 2z equals to 4, and then y minus z equals to 10. So here we go, 3 equations, 3 unknowns again. How should we solve it? So let me suggest for this one that what we should do, I mean, there's different things you could do. Let me suggest one thing we could do would be we can pretty much see from the first equation, or if you like the second equation, right? If we take this one and divide by 2, what happens? We get what? X plus y plus z equals to 2. What does that show us? Yeah.
Those 2 equations are the same.
That's right. They're the same equation. So do we need to keep both of them? Not really. We can just focus our attention on, like, for example, the first and the third equation, right? So so we can just keep the, or if you like, we could kind of like subtract 2 copies of the first one from the second one. We get 0 equals 0, so yay. Anyway, just to recap here, we've got x plus y plus z equals to 2, and y minus z equals to 10. All right? That's really the same as the given system, right? Because the first 2 equations are the same equation, so dropping one of them doesn't change anything, does it? When I say 2 equations are the same, what do I mean by that? How do you judge the sameness of 2 equations?
Represents the same line.
Presents the same, what?
Represents the same line.
Represents the same line, but these are planes. And if we have 4 variables, they could be like hypervolumes, and if we had 5 variables, whatever. I mean, they're linear objects of higher dimension, but yeah.
But they have infinite solutions when you compare to each other.
They have infinite solutions, yeah. I'm asking a more simple question. It's actually a question that still makes sense even for nonlinear equations, which is, when do you say 2 systems or 2 equations are the same? Like, what does it mean for 2 equations to be the same equation? Like, how do we judge that? That's a kind of loaded question, but I would say that 2 equations are the same when they have the same solution set. right? So like in algebra, we learned that if we take an equation and we like square it, it's not exactly the same solution because we can add those extraneous solutions, for example, or like when we use log properties, we combine logarithms, we can simplify the equation in such a way that it's no longer technically the same equation, because in using the log properties, we've assumed something about the solution which may not actually be true for the original problem. So anyway, long story short, to say two equations are the same is to say that they have the same solution set. So the question we have to ask ourselves is, what things can we do? What can we do to a system of linear equations and not change the solution set, right? Because that's what we'd like to do. We'd like to do things where we're not losing solutions, we're not gaining them. The modified equation is the same equation in that sense. It has the same solution set, right? So like dropping redundant equations, as you pointed out, that's fine, right? What can we do here? To sort of see through the noise, what do we do?
Set y equal to something and then plug that in.
So you're thinking substitution. Set y equal to something and plug it in. That is certainly an option. So y is equal to 10 plus z. And that would then give me that x plus 10 plus z is equal to 2. Oh, plus z, my bad. I lost a z. 10 plus z is equal to 2, which then we could solve for z, for example. I guess we could solve it for x, that's easier. X is equal to 2 minus 10, which is minus 8, minus 2z. All right, great. And what's y equal to? Well, we already figured out y is equal to 10 plus z, right? What's z equal to? Well, apparently z, all right? So the given system is equivalent to this system. Let me make it a little bit more explicit here. So our solution set, which that was supposed to be a curly. My curly brackets are they're devolving solution set. So we've got minus 8 minus 2z, 10 plus z, z, such that z is a real number. For those of you who've had Calc 3, what we're looking at geometrically is that these three planes are actually two planes. They intersect in a line of intersection. The line of intersection has parameter z. And this is a parameterization of said line. Now, this solution set, warning, not in standard form. I don't think it is. Is that standard form? Goodness, I don't know. I don't want to get you guys into bad habits here, because I hope you're starting to get the feeling like, well, this is kind of okay, but it's not very neat and tidy, and there must be a better way. And the answer is yes, there is a better way. It's called row reduction. So I regret erasing that. Because I could have shown you that in row reduction. Oh well. Let's do this one. So we can introduce what's called the augmented coefficient matrix. The augmented coefficient matrix. And so like for example 7, the augmented coefficient matrix for that, it would look something like 1, 1, 1, 2, 2, 2, 2, 4, and 1 minus 1. There's a 0 over here, and 10. All right? So that's the augmented coefficient matrix for this system. You notice the advantage here is you don't have to write the variables. It's understood, right? Now there could be situations where there's an ambiguity, in which case it's customary. If there's ambiguity, what you do is you write up here x, y, z, just to be kind to your reader and to announce to them, hey, that's the x one, that's the y one, that's the z one. All right? Okay, and then you can do operations on the augmented coefficient matrix which correspond to the things we've been doing to equations. Like, for example, I can take row 2 minus 2 times row 1. And that will get me 1, 1, 1, 2, 0, 0, 0, 0. 0, 1, minus 1, 10. All right? So this is called a row operation. It corresponds to one of those things we can do to an equation and not change the solution set. What are those things? Well, one of those things is add an equation to another or subtract equation from another, right? That's one of the allowed elementary row operations. And the next row operation is kind of silly, but here it is. We can do row 2 swap, a row swap, row 2 and row 3. And this is a very, I think it's hard to understand what this is without the augmented coefficient matrix way of thinking, because like this is just relabeling them, right? This is saying equation 2 and we're switching the labels for equation 2 and 3. Now equation 3 is equation 2 and equation 3 is the other way around. Yeah, words. All right, and then what? Well then, my final move here I would do row 1 minus row 2. And when I do that, it gives me 1, 0, 2, 2, 0, 1, minus 1, 10, 0, 0, 0, 0. All right. This is called row reduction. The things that we're allowed to do are to add one copy of a row to another. We can scalar multiply a row, and we can swap rows. I'll say this more carefully next class, and I'll give you a handout that gives you the full story, all right? And we'll do more examples, obviously. But this is a far more orderly way of solving systems of equations, because it's going to get us to a standard form for the solution, right? Like this final system right here, it corresponds to what? X plus 2z is equal to 2, y minus z is equal to 10, and nothing. Nothing. And so, in other words, solving that again, rewriting that, we have x is equal to what? Oh man. Yeah, fine. I'm sorry, I got distracted. X is equal to 2 minus 2z. Y is equal to 10 plus z. And z is equal to z. Isn't that what we found? Ah. Oh? How did I get that 8?
I think
Which one's wrong, me or?
you did R1 minus R2, you didn't subtract the...
Oh, my bad. So R1 minus R2, where's I said the one? 2, oh yeah, what's 2 minus 10?
minus 8.
Yeah, that'll get you. So let's put a minus 8 there, thank you. And see folks, if we go through this algorithm, see, when you have a problem like this, you could just as well have written the answer in terms of y rather than z. In fact, you could have written the answer in terms of x, y, or z here, right? But the standard solution is as what I've boxed in here. If we go through this algorithm, there is a distinction between the variables. The variables which appear in so-called pivot columns are always going to depend on the variables in the non-pivot columns. But now I'm getting ahead of the story. That's what we'll talk about next time, I think. So I think I'm out of time. Yeah, I'm out of time. Anyway, thanks, guys. Yep.